Hello, everybody. I hope everybody is fine. And in this video, I'll be talking about Bohr approximation. And this Bohr approximation is basically a method that's used in quantum scattering theory. Quantum scattering theory. And why it's used basically to approximate the scattering amplitude. Scattering amplitude. When the interaction uh, potential is weak, and we call it we would like to go with the first Born approximation, and it gives the leading order term in perturbation expansion of scattering amplitudes. Now, in this case, we will try to come from the upper side to go down to the lower side. So here I would like to use what we call as Lippmann-Schwinger equation. This will be our starting point, and from here we will move on. And this Lippmann-Schwinger equation in scattering theory, it provides a formal solution basically to the Schrodinger's equation. And especially the solution to the scattering potential. And if that scattering potential is scattering potential, say that is V of R. And we can immediately write Schrodinger's time independent equation with a particle having an energy E. So that will be H psi is E psi, where this H is H naught plus V. So this H is our total Hamiltonian, and it's a function of unperturbed Hamiltonian. It's a function of Hamiltonian and the potential. And if we have free particle, I should call it free particle Hamiltonian. Free particle Hamiltonian, which only accounts for the kinetic energy. So this H naught is nothing but H cross square by 2m and d2 by dx2, and this is my free Hamiltonian, free particle Hamiltonian. And V of R is the scattering potential. Scattering potential. And it's a wave function of the system, the state of the system, the eigenvector of the system. So eigenvector or a wave function. Now the Lippmann-Schwinger's equation for this scattering of psi k. Now psi k gives us the measure of scattering, and this psi k is state k plus 1 by E minus H naught plus I epsilon V of psi k. Now this state vector k, it's basically a free plane wave state. It's a free plane wave state. And this whole thing, so I should write here, this is my plane state wave, plane wave state. Okay, and then the next term is 1 by E minus H naught, then plus I epsilon. This thing is Green's function. And we can represent it by G naught of E. Now this equation that I have written down here, this equation expresses the scattering psi of k as the sum of incoming free particle state. So this k is a free particle state. It's an incoming particle. And the sum of this state and the correction due to the interaction with the potential. And if I write down the quantity we are interested in, basically in scattering amplitude. So if I write down scattering amplitude, f of k dash and k. So these are two momentum states, and which is related to the probability that the particle with initial state k is scattered to the final state k dash. And the scattering amplitude that we have, okay, we have the scattering amplitude, and it simply deliberates the scattering from the state k to k dash. And this scattering amplitude is given by the matrix element. It will be given by the matrix element of the potential. So the matrix element of the potential, suppose that potential is V, but what will be the structure of that matrix element? The structure of that matrix element will be between the free plane wave state to the scattered state. So if I have to write this F, what's called as scattering amplitude, as k dash, as a function of k dash and k, this must be equal to minus m by 2 pi h bar square k dash, then v, then if I define it, so the point is I want to define this scattering amplitude from the scattering state. And what's my scattering state that I'm trying to define here is psi of k. So here I must have psi k from the state psi of k, from the state psi of k to k dash. Now this is my expression for scattering amplitude, and that can be calculated by simply calculating the matrix element of the potential between psi k and k dash. Now if I use the Lippmann-Schwinger equation for psi of k was here, okay, this is my psi of k. If I use this this equation for psi of k, what will happen to this equation? I will have f of k dash k equals minus m by 2 pi h bar square, then k dash v and k minus m by 2 pi h bar square 2 pi h bar square. Then what's left is k dash then v of 1 by e minus h naught plus I epsilon. Close, and psi of k. Okay, I think I have done something wrong here, because here I have my own v, okay, and here in the equation I have here v, so v should come 2 times, so I should correct it. It's not visible, so I will write it again. So f of k dash k, the scattering amplitude, is minus m by 2 pi h bar square, then k dash v of k, then minus m by 2 pi h bar square, then k dash, and using the Lippmann equation, we have v times 1 by e minus h naught plus I epsilon, and here I have v and then I have psi of k. That's the case. Now this is the full expression for the scattering amplitude. And to proceed, what we want basically is we want to make the first Born approximation. And first Born approximation is a simplification to this equation. And moving from now, the first Born approximation, what it does basically, it assumes that the scattering potential is weak, as I said. Scattering potential is weak. So if it is weak, I should say it's weak enough that we can neglect the multiple scattering events. This means that we can replace the exact scattering state that we have, psi of k, by the free plane wave state k. And what's that? In the second term of Lippmann-Schwinger's equation. All right, so what we are going to get, so if we take that down, that part, what we get is the first Born approximation. So what's that? That is f of k dash k is minus m by 2 pi h bar square k dash v of k. Now, this simplifies the problem, and it simplifies the problem to a very large extent, as the scattering amplitude is now just a matrix element. It's nothing, a simple matrix element. And the matrix element of what? It's the matrix element of the potential between the two free states, k and k dash. Now, the wave function for these plane wave states, what are those wave functions? If I take r as the position, if I write down the wave function, wave function as r state k, this is over 1 by 2 pi whole raised to power 3 by 2 e to the power of I k dot r. And similarly, I can write down I r k dash as 1 by 2 pi whole raised power, this is 3 here, 3 by 2 e to the power of minus iota k dot r. Thus, the matrix element that we have here, we can write down this matrix element as, what's it? It is k dash, then v, then we have k. This is equal to integral of k dash r and v of r and r of k and dv or d3r. All right, very, very simple. all we are doing is we are making use of the wave function r of k and r k dash in our matrix element. So by calculating this matrix element, we are actually calculating the scattering amplitude. And uh, and and what we do, we substitute the wave function in this integral. So when we do that, what we come up with, when we substitute the wave function, we have 1 by 2 pi whole raised power 3 by 2. Then we have integral. Then we have e to the power of minus I k dash dot r. Then we have v. Then we have e to the power of I k dot r. And then we have d3r. That's the case. Now, what is this? This is simply the Fourier transform. It's the Fourier transform of v of r, and this is the Fourier transform of the v of r, and we can have here, if we have evaluated at q, if we take some q as what is it? I have k dash and I have k. If I define q as k minus k dash, this k minus k dash is giving me the measure of what? It is giving me the measure of momentum transfer. It's giving me the measure of momentum transfer. So if I proceed from here, okay, so what should I write? So writing down my matrix element, that gives me the measure of this, what we call as scattering amplitude for Born approximation, and this will be 1 by 2 pi whole raised power 3. And because when you multiply the two, you will have raised power 3, and then what you will have is integral e to the power of I will be out, and I'll have k minus k dash and dot r, then v of r, okay, and we can write down this as equal to 1 by 2 pi whole 3, then v of q. Now, where this v of q is what? Is the Fourier transform of the potential. So where v bar of q is Fourier transform of potential v of r. So what is this v bar of q? It is integral e to the power of I q dot r, because I have already defined this k minus k dash is q dot r v of r. So what is the beauty of this equation is that we say that the scattering amplitude in the first Born approximation can be written, okay, so scattering amplitude in first Born approximation, that will be f of k dash, and k, this is my scattering amplitude, that is minus m by 2 pi h bar square. I don't care about it, this is just a number, and then I don't care even about 1 by 2 pi whole cube. It's simply v bar of q. So it means if you take the Fourier transform of the potential and multiply it to this number, you're going to get the measure of the scattering amplitude. Now, the final expression for scattering amplitude in the first Born approximation, which I have written over here, okay, and this is what is called as Born formula. You can call it Born formula. And this Born formula, what it does basically, it expresses the scattering amplitude as a Fourier transform of the potential Fourier transform of what? Fourier transform of V of R, evaluated at the momentum transfer. And what's that? Q is K minus K dash. Now, if we go with some special cases, I mean, let us choose a spherically symmetric potential. Now, let's extend this this approximation to a spherically symmetric potential. Spherically symmetric potential. Now, if the potential is spherically symmetric, if this V of R is spherically symmetric, then V of R is simply V of R. That is, the Fourier transform can be simplified using spherical using spherical coordinates. I mean, in this case, the Fourier transform of the potential V of Q bar becomes simply 4 pi 0 to infinity R square dr, then V of R sine Q R by QR. And see the beauty of the situation here, that when we have the spherically symmetric potential, then we can also simplify the Fourier transform, and it can be simplified using spherical polar coordinates and the equation that's out there, and you can turn down the things in terms of R and QR, where this Q that's written over here is nothing but the magnitude of K minus K dash that I have already defined. So substituting this bone, substituting this into the bone formula gives us simply the what we call scattering amplitude. So when we will use the value of this Fourier transform V bar of Q in this equation, it will automatically give us what? It will give us scattering amplitude. It will give us scattering amplitude for spherically symmetric potential, and that I should put down that will become a big equation. Now all you have to do is to substitute the value of V bar over here. So the equation that we will have will give us the measure of the scattering amplitude for spherically symmetric potential. And now I would like to conclude my talk. Now I would like to summarize this talk, and what Born approximation is, it basically provides an approximate solution to the scattering problems, okay, by assuming that we have a very weak interaction potential. The potential is assumed to be extremely weak. The first Born approximation leads to a simple expression for scattering amplitude, as you can see, as you can see here, by just putting the Fourier transform of the spherically symmetric potential or any potential into this equation to calculate this. So all you have to do is to calculate the Fourier transform of the potential, and this is what is widely used in quantum scattering theory to estimate scattering cross sections and other observables. So with this, I would like to say you goodbye.